Hey everyone, welcome back to my YouTube channel. We know there are different ways to solve a problem, and we need to learn how to compare different algorithms and pick the best one. In this video, we'll be talking about two metrics that are used to analyze the performance of any given piece of code or algorithm, which are time complexity and space complexity. Let's have a look at both of them. Time complexity is defined as the amount of time taken by an algorithm to run as a function of a length of the input. Time complexity is not the same as the runtime of a program. The amount of time needed for execution is a mathematical quantity, so we represent time complexity mathematically using asymptotic notations like big O, big omega, and big theta. Let's understand the difference in these three asymptotic notations. Starting with big O. Big O is defined as the upper bound, and the upper bound in any algorithm is the most amount of time required, which is the worst case scenario. So if we talk about a linear search, where we are searching for one element by visiting each element one by one in an array, then the worst case is that we'll find that element at the end. So by big O notation, the time complexity for a linear search will be big O of n, where n is the length of the input. The big omega notation is defined as the lower bound, and the lower bound in any algorithm is the least amount of time required, or we can say the best case scenario. Taking the same example of linear search, the best case will be that we find the first element as the required element. So by big omega notation, the time complexity of a linear search will be big omega of 1. Big theta notation is defined as the tightest bound, and the tightest bound in an algorithm is the best of all worst case times that an algorithm can take. Let's try to deduce the time complexity of some example codes. In this code, there's only initialization, input and output statements, an arithmetic operation, and a return statement. All these statements have a time complexity of big O of 1. So the time complexity of the entire code is big O of 1. That means it is not dependent on the input, and we call this complexity as constant time complexity. In this code, there is a for loop involved. Apart from the for loop, the rest of the lines have a constant time complexity of O1. The for loop will run n times, which is the length of the input. So its time complexity will be big O of n. The entire code will have a complexity of big O of n plus 9, where 9 is the constant complexity for the lines other than the for loop. But the constant is usually neglected for large values of n, and in big O notation, the time complexity of this piece of code will be On, and this is also known as linear time complexity. In this code, to get the sum of a square matrix, we're using a nested loop. So we have one for loop and then another for loop which is inside that for loop. So that means the first for loop will run n times, and then the inner for loop will again run n times for each value of the above for loop. So therefore its runtime complexity will be n squared, which is n into n. The entire code will have a complexity of big O of n squared plus 9, where 9 is the sum of constant time complexity of the remaining statements. And again we'll ignore 9, and the complexity of the entire code will be big O of n square. This is also known as quadratic time complexity. Now this is a good one. Here we can see we have one loop, but inside that loop we're actually dividing the n by 2. So if I pass 8 as an input to this function, instead of running 8 times, it's going to give me the output 8, 4, 2, 1, because after each execution, it's dividing n by 2. So such algorithms that break a number or a set of number into halves fall under logarithmic complexity. So in big O notation, the complexity for this piece of code will be O of log n. Now let's talk about space complexity. Space complexity deals with the amount of memory required in a system for execution of the algorithm. It is the sum of the space required by the input as well as the extra space used inside the algorithm. Let's have a look at some examples and try to deduce the space complexity of those examples. In this code, 3 integer type variables are used. Now, the size of the integer, let's say it's 4 bytes. So the total memory required for this code will be 4 into 3, that is 12 bytes. And it will not change based on the input given by the user. So the space complexity for this piece of code is big O of 1, which is again a constant space complexity. Now in this piece of code, we have some single integers as well as we have an array of dynamic size n. So the total memory required here will be, again let's assume int requires 4 bytes. So we'll need 4 bytes for n, 4 bytes for sum, and 4 bytes for I, that is 12 bytes. Plus, for each element inside the array, we'll need 4 bytes. So the total space required here will be 4n plus 12. And in asymptotic notation, we'll denote it as big O of n, which is linear space complexity. The amount of space required by this program will increase linearly as the size of the input increases. The factor of time is usually more important than the factor of space because you can always get more space by upgrading your hardware using a bigger sized RAM, but there's nothing you can do to buy more time. So if we have to do a sacrifice, like if I can reduce time by using some extra space, we should go for that. But we should not do the reverse. We should always aim for best timed algorithms. I hope I was able to clarify the usage of space and time in algorithm analysis. From the next video onwards, whenever we'll use an algorithm, we'll try to gauge its time and space complexity, and I'll share it with all of you. If you like this video, please share it with your friends and subscribe to the channel for more learning content. I'll see you in the next one. Peace out.